Assalamu alaikum. Welcome to the series of lectures on advanced computer architecture. In our last lecture, we discussed the comparison of a number of sample processors like SRC, Falcon with its two versions, Falcon A and Falcon E, and Eagle. All of these processors were basic examples of a RISC philosophy. The reduced instruction set architecture just facilitates to have simple instructions so that we can execute each instruction in approximately one clock cycle. The number of instructions are restricted. The number of addressing modes are limited. Out of this simplicity, we achieve a better performance. Although all these processors are examples and simple hypothetical processors, but still these are just good examples to illustrate the idea of ISA design. For a designer, he can just see and choose different instructions depending upon a particular application. So if it is a general purpose application, then the set might be slightly different than for a dedicated application. So comparing these three or five different processors, we said that the factors like how many operands are there, where the operands are stored, how the memory is accessed, and what are different addressing modes available in a particular processor. This would determine the overall concept of this ISA. ISA is extremely important, and that is the first step for designing any particular processor. All of these processors were examples of a RISC philosophy, meaning that the reduced instruction set would enable that we could, in a shorter time, in a shorter clock period, execute almost all the instructions which one has selected, which the designer has selected, as against the CISC philosophy, where we said that the instructions are more complex, the addressing modes are varied, and there are a number of variety of addressing modes. In the case of RISC machines, the variety is limited, and then it gives usually a better performance as far as RISC is concerned. After going through these example processors with hypothetical instruction set, let us today look at some examples, and one example of a RISC processor is a Spark machine. The Spark, which basically was announced by Sun Microsystems in 1987, and this is primarily stands for Scalable Processor Architecture. It was less of a microprocessor design rather than it was an architecture. So it is an open architecture in the sense that under license, different semiconductor vendors manufactured and implemented this architecture on different media using, for example, CMOS or ECL and gallium arsenide. So in different implementations, the basic philosophy of Spark architecture was maintained. We will discuss some of the features of this Spark machine again with the help of some slides. But before we go to some details, we can just look at the broader features of this Spark processor. The Spark processor is an example, a practical example of a RISC philosophy. The instruction word is 32 bits. Now, it's generally a general purpose register machine, and there are 3 processors available. First of all, we have 32 registers, each of 32 bits visible at one time to the programmer, and this is the integer unit. The second set of registers implements the floating point operations, and the third one is available as a coprocessor for the user to implement specialized functions. Now, the accessible memory range is 2 raised to power 32, which is implemented as a virtual memory, and the addressability is 2 raised to power 32. Now, apart from the main registers, we have other special registers which we'll see in our programming model. As other RISC machines operate, the interaction with the memory is through the load store concept. That means any data which is to be fetched from the memory, we will use a load operation, and when we want to place the data into the memory, we'll use the store operation, as we have done in the example processors. Now, the key concept, which is not there in all the processors which we have discussed so far, and that is the array of registers, or we can say the concept of register windows. And that is an extremely important concept, and is peculiar to this Spark processor. We will illustrate that with the help of some slides, but briefly you could just say that the implementation of register windows would reduce the time of procedure calls. So you could say a rolling set of registers which are altogether 120 in numbers, each one of 32 bits, that formulates a sliding window. And the out of these 120, the first 8 registers named R0 to R7 are for global variables. These global variables are common to all procedures. And then we have input parameters, the output parameters, and then the passing on parameters to the procedure through a sliding window, which each would occupy 8 bytes. So altogether we'll have, 8 words, and altogether we'll have actively 24 registers involved in the window operation. Let us look at a few slides to illustrate these concepts about the Spark processor. This slide shows the programming model for Spark processor. As already indicated, here we have one set of integer registers named just from R0 to R31. Each is 32 bits. Then we have a set of floating point registers, also numbered from 0 to 31. We have 2 program counters, PC and NPC. The program counter PC and NPC hold the current and next instruction addresses. The process status registers, PSR, contains the flags or condition codes. The user programmable registers here are not indicated, and these are basically called coprocessor registers, and the user could in fact put special functions in these registers. We will not go into the details. The idea is not to make you an expert on the assembly programming of Spark processor. Rather, we would just like to highlight some of the additional features or the differences as compared to our simple example processors. In addition to these registers, we have some other special purpose registers like WIM, TBR, and multiply step register. Now, looking at this program model, you can just see that we have WIM is the window invalid mask register, and TBR is the trap base register, and we have multiply step register. Now, this programming model would be illustrated with the help of a couple of examples in one of the later slides. Now, we have just said that the total memory space available with the Spark is 2 raised to power 32 bytes. The word size is 32 bits. The memory access could be 1 byte, 2 bytes, 4 bytes, or 8 bytes. The storage format is big endian. The concept of Spark register window mechanism is shown in the following slide. This is the key concept and the most important difference between the processors which we have discussed so far and this real RISC processor. We said that altogether in the original version of Spark, although it depends on the actual implementation, but this is just an example of what was implemented in the first Spark machine. R0 to R7, written as global registers, indicate and store the values of global variables. And then the current window, for example, at the top addresses from R8 to R31, the 24 words store. Each window contains 32 registers, 8 for global and 24 for the local or input-output parameters. We have input parameters passed on to a procedure, then output parameters taken out of this procedures, and then 8 words for the local variables to that particular procedure. This window slides and it is indicated by the current window pointer, which is in one case on the leftmost side it is N, and when we just let us say restore or we just call, we move it to N-1, then to N-2, so it is a sliding window. And at the end, you can just imagine that this set of registers is close together. So from the last, when we reach the last one, we come back to the original index position. The Spark concept on overlapping register window avoids the procedure delays, and so call and return would be avoided and almost delay would be 0 in this case. Using register windows, parameters are passed between procedures at 0 cost. There are primarily 3 addressing modes available with Spark: immediate, register addressing mode, and relative addressing mode. Other variants are derivatives out of these 3. The set of instructions could be divided into 3 functional groups. The data movement group. Secondly, we could have arithmetic and logic group. And thirdly, the program control instructions. All these instructions, as already indicated, would have 32 bits. So each instruction would be 32-bit long. There are three main categories of instructions as far as format is concerned. So I hope you remember that we had a variety of different types which we called type 1, 2, 3, 4 or A, B, C, and in this case we have 1, 2, 3, and there are two variants, could be 2A, 2B, 3A and 3B, that we will illustrate with the help of a slide, the format of the instruction set available in Spark. There are three instruction formats as shown in this slide. The first one has an opcode followed by a displacement. Example could be a call. Then in second category we have two examples, 2A and 2B. It is followed by, opcode is followed by a condition and then an opcode for mode 2 and displacement with 22 bits in each case. In the third type, we have examples like floating point operations, data movement, and arithmetic logic instructions. Again, opcode followed by the destination register and source registers with different variants are available in these instructions. These instructions are further illustrated in the next 4 slides, divided according to the functional group. The first slide shows examples of data movement instructions like load and store. It could be load or store byte or word. It could be signed or unsigned. The details at this point may not be so relevant, and one could always go through the actual table if it is so required, or later on use the assembler for the Spark to work with these instructions. The second group is the arithmetic instructions. We have add x, subtract, and subtract x, and multiply with the sign multiplication in this case. The third table indicates the detail of logic instructions. We have AND, OR, XOR, and other instructions of shift left and shift right. The last one indicates the branch and control instructions, where we have branch, jump, call, save, and restore instructions. The save and restore would be utilized along with the register windows as already explained. Now you just have an idea of the Spark processor, which is a RISC philosophy, and you can appreciate now, comparing this real processor with the example processors which we discussed earlier, that there are many things in common, like load store concept is common, like the instruction set, each instruction occupies a fixed length which is 32 bits in this case. However, on top of that, there are some additional features which have been introduced, and that gives programmer a facility to have a better performance, like the condition codes, and there is a status register which tells us different parameters like if 0 or negative or positive. These details at this time are not important because we are interested not in assembly language programming. This is not a course on assembly language programming, rather this is a computer architecture course, and we just want to see that what are the programming facilities available to a programmer which an architect has to provide. So therefore, just try to visualize and compare the instruction set of Spark with the instruction set of the previous processors which we have discussed, and then in particular appreciate the use of status register and the use of the register window, which is a key concept, and that really gives a lot of benefit wherever the procedure calls are concerned, and the overheads would reduce, and we will get a better real processor as compared to the example processors which we have discussed so far. Now the RISC processors, we have considered both examples for the hypothetical processors as well as one example for the real processor. To appreciate the differences between the RISC and CISC philosophy, let us also go into some detail for some examples of CISC processors. We will, in the following material, we will cover two of the processors, one from Motorola and the other one for Intel. The Motorola processor is given in detail in your textbook, and we will just quickly overview the Intel processor and see that what are the major differences between the CISC and the RISC design philosophy. You remember from one of the earlier lectures, we said that in the case of CISC, the complex instruction set would give a flexibility, and one could do a lot of complex jobs, complex operations by using just one instruction, which in the case of RISC, we would probably need a number of instructions to implement the same function. So it depends on the designer. The cost-benefit ratio would depend on a particular application, and we could do the same job both with RISC or with CISC. In the case of CISC, as we said, we will have usually a variable length of instructions. So some instructions might occupy just one word, others two, or maybe three. And as compared to a RISC machine where the addressing modes are limited, we have a lot of addressing modes, 14 in the case of Motorola. This Motorola 68000 family was introduced in 1979. It's a 32-bit machine. Now, by definition, we could just say that the majority of instructions in a processor correspond to 32 bits. The data path is 32-bit in this case. And, well, the data transfer may be on byte basis, or we could have 16 bits or 32 bits, but majority of the instructions utilize 32 bits as an operand. And that's why we just call it a 32-bit machine. It has one processing unit. It has a variety, hundreds of instructions, and variable length of instructions is available in this case. And as I said, the addressing modes are different. Now the registers, it's a variant or a generalized version of general purpose register machine. So the number of registers in this case are divided into address registers and data registers. We have 8 address registers and 8 data registers. We designate the data registers like D0 to D7 and address registers as A0 to A7. The program counter is also 32 bits. However, the addressability is not 32 bits. It has only the first 24 bits which are available for addressing the memory. So therefore, the maximum addressable memory or the memory resources would be 2 raised to power 24. It's not 2 raised to power 32, rather it's 2 raised to power 24 because the designer has just given the option of using only 24 bits. IR register in this case is a 16-bit register. So that would mean that you will be able to decode only the instructions having 16 bits. If we have longer instructions, then we will fetch another 16 bits and then decode it cyclically one after the other or together, depending upon the instruction format, which we'll see later on in one of the later slides. Now, similar to what we had in Spark, in this case, the condition code register or status register is also available. It's a 16-bit register, and we could say that there are 2 bytes. The lower byte is the user defined and the other one is the system defined, let us say, byte. So we'll look into a little bit more detail, and let us see in the next slide the programming model of this Motorola 68000 family. This slide shows the programming model for 68000 processor. Now, as already stated, there are 2 sets of registers. One we call data registers from D0 to D7, each of 32 bits. The second set is the address registers from A0 to A7, also of 32 bits. PC is the program counter having 32 bits, but only the lower 24 bits are used for addressing the memory. IR register is a 16-bit register, and CC is the condition code or the processor status register. The next slide shows the addressing modes available for the Motorola family. You will see in this case, as already stated, there are 14 different addressing modes. The second column shows the RTL notation, and the last column shows the operand location. Like the first entry, the first row is an example of data register direct. Notation DN means the data register N, where value of N is from 0 to 7, D0, D1, and so on. And the operand is available in this data register straight away. So we have DN as the operand. Second entry is address register direct. That would mean now instead of data register, we have address register AN. Again, N ranges from 0 to 7. The next one is address register indirect. And now you see that AN within parentheses would mean that now we point to a memory location as given in the register AN. For example, A2 within parentheses would mean that we need to fetch and address the location in the memory given by the contents of this address register A2. Similarly, we have the next addressing mode as auto increment, AN within parentheses plus. This would mean that we fetch the contents indicated by the address AN and then also increment the contents of this address register by the word size WS. So semicolon would mean that one after the other. First we fetch the contents from a location indicated by AN and then increment AN by the word size. For example, if it was 2 bytes, WS would be 2, and if it is 32 bits, WS would be 4. Similarly, we have auto decrement, then we have based, index, short and long. I need not go into the detail of all these addressing modes. You could just have a practice and go through it. These are given in your textbook. The next slide shows the instructions which we have available with MC 68000. The first type of instruction is a single word instruction. We have opcode with 4 bits. Then we have register 2. RG2 represents the register mode, and then MD2 as a mode of that register. Similarly, MD1 and RG1. Now the values of RG2 and MD2, which are 3 bits each, are available in the table given in your book, depending upon different instructions which would use this data. Now you could just say we have opcode field 4 bits, then we have mode field MD, and the register field RG. So there could be, for example, in one case, 1 and 2 might refer to the source and destination indicated. Now this is a single word instruction with 16 bits. The next one, we have 2 word instruction, and after the 16 bits we have another 16-bit constant with extra word. Similarly, the third type is a 3-word instruction followed by 2 16-bit constants. And the last one is the instruction with indexed address. The following slide shows the behavioral RTL description for an example which corresponds to move instruction. For the move instruction, the opcode followed by the information of 2 registers and the mode information is indicated in this slide. When opcode is 0, then we have the result dependent on MD2 and RG2. This defines the temporary location, and we say the opcode defined by MD1 and RG1 is shifted to the result field defined by MD2 to RG2. As a result, the data in MD1 and RG1 define the effective address of the source operand, and MD2 and RG2 define the destination operand. So as a result, for this move statement, we fetch the data from the source to the destination operand. The following RTL description gives the complete information regarding also the setting up of the flag bits Z, C, N, and V, which is evident from the information given in this slide. The next slide shows the behavioral RTL description for load effective address instruction LEA. This is used for complex address calculations and corresponds to an opcode defined by binary 0100, which means either opcode is decimal 4 or the mode 2 is 7. If this condition is met, then the effective address calculated based on MD1 and RG1 is placed into the address register given by 2, as in this example A within the square brackets register 2. The effective address, not the contents of the memory, is loaded into location A. Now for Motorola processor, the instructions could be divided in 3 conventional functional groups. The first one, you could say, is the data movement or data transfer instructions. The second group is the arithmetic and logic instructions. And third one is the program control instructions. Let us illustrate the use of these 3 groups with the help of some tables and some examples. We look at the following slides for this concept. This slide shows some commonly used data movement instructions. The first column indicates the mnemonic, the second column the opcode, and third one the operation, and then fourth one the operands, and last column indicates the size of the operand. We'll just take a couple of these instructions and see how to interpret. The first one is move.b. The opcode in this case, which is 4 bits, is 0001. The next 6 bits indicate, in this case, the information about the destination. I hope you remember from the previous information that this data D would be available from one of the tables, and this would calculate what is called the effective address of the destination. In the operands column, it is indicated as EAD, meaning that effective address of the destination. Similarly, the 6 bits indicating SSS, that shows the source operand, and we need to calculate the effective address of the source operand using the information of the mode and the register available in one of the tables given in the book. And this particular operation would mean that the contents from the source are taken to the destination. From where to fetch, that would be available. The data would be available from 6 bits from bit number 0 to 5, and the destination would be so on the next 6 bits. Similarly, the next instruction is move.w, which is a word operation, and you could just interpret in the same way, except for the fact that instead of byte, we are now transferring or moving 2 bytes, which is a word. And next one is a long word consisting of 32 bits. You could just interpret other instructions exactly in the same way. The next table shows the group of commonly used arithmetic and logic instructions. Exactly in the same way, we have 5 columns with mnemonics, opcode, operation, operands, and the operand size. The instructions are add, subtract, compare, compare immediate, and multiply signed, division signed, and or, exclusive or, and so on. Now, the interpretation is quite evident, and you should just do it as an exercise at home with the information given in your textbook. The next table shows some shift and rotate instructions available in Motorola processor. Now in this case, we have arithmetic, shift, rotate, and other instructions. You could just see the operands available are also indicated in the third column along with the mnemonics and opcode. The next table indicates the conditional instructions, and we have BCC, DBCC, and SCC, and the operation just shows that if the condition is fulfilled, then we have a displacement operand which is a part of the instruction, and the PC would be updated by a displacement figure or otherwise by 2 or 4 depending upon the corresponding data available in the instruction. The next table shows the branch instructions. These are the unconditional branch instructions. BRA, for example, would just point out and PC would be moved to PC plus the displacement figure given following the opcode. So we have other jump and branch instructions. The operation is indicated using the RTL notation. Just to give you a flavor, we have discussed the Motorola 68000. We have just a feeling of what are different addressing modes, what is the length of different instructions, and what are different groups of instructions available in Motorola 68000. You can realize by now that as compared to RISC, the number of instructions available are much larger. Similarly, the addressing modes are also higher. We have 14 different addressing modes. There is a lot of flexibility to the programmer that an ISA designer has provided. But at what cost? The cost is a longer duration of evaluating and executing different instructions. Some instructions might be executed, for example, in fewer cycles, clock cycles, and some other instructions might require a much longer number of clocks. Now, how many clocks are required, and this complete data is available to you in the form of tables from the manufacturer, depending upon which family of Motorola you are using. In most of the desktop machines, it is the RISC processor which is used. We will now consider another example of a CISC, and that is the Intel family. You are quite familiar with this through another earlier course. You have done the assembly language programming with Intel. However, we will just browse and see the important features available with Intel and just to make a comparison with what is available with Motorola. We'll not go into the exact details of the assembly language programming which you have earlier done. Rather, we'll just look at the availability of different features with the ISA of Intel. In the case of Intel architecture, we have data registers consisting of accumulators, base index, count, and data registers, and the control registers in the form of instruction pointer and the flag and E-flag control registers. There are 4 segment registers and 4 special registers. The segment registers, each of 16-bit, is code segment, the data segment, the stack segment, and extra segment. Through these segments, we have a possibility of relocation, and the code could be made really relocatable in a way the programmer would like. Similarly, the stack pointer could be used for implementation of stack, and base pointer for the base index addressing mode, and so the other registers. The programming model for the Intel machine is shown in the following slide. Now you can just see all these registers indicated in the programming model. We will again not go into the real details because most of you are familiar with this programming model and you have already worked with the assembly language programming of the Intel family quite in detail. 32 address pins give us the possibility of addressability of 2 raised to power 32. So we have a total memory resources available from addresses 0 to 2 raised to power 32 minus 1. The storage into the memory is little endian. As compared to what we had in Motorola, it was a big endian, and in Intel it is little endian. That means most significant bit at higher address and lower significant bit at lower address. Then the soft alignment is also a feature where the alignment is not required. So that means in the case of storage, we need not have an address which is divisible by 4 or by 2 as it was in our example processors of SRC or in the case of Falcon. In this case, since we have a variable length code, so we need not have an exact multiple of the addresses where we want to put our code. So it is a soft aligned possibility. Alignment of addresses is not a necessity. Now we look at what are the different addressing modes available with Intel and the general format of the instruction set. This slide shows the 7 addressing modes supported by the Intel processor. The first mode is the register direct. The second one, a base with 8-bit displacement or a base with 32-bit displacement. The third mode is the indexed addressing mode. Fourth one, based index plus 8-bit displacement or based index with 32-bit displacement. The fifth mode is base plus scaled index with 0, 8, 16-bit possible displacement. The sixth one is 32-bit direct, and finally we have the possibility of using an immediate mode where the operand is specified in the instruction. The general format of the instruction is shown in the next slide. The length of the instruction could vary from 1 byte to 17 byte. Generally, we have a prefix which was introduced in Pentium, followed by an opcode. The opcode is 6 bits long. Then we have some information about address specifiers. For example, some of the bits out of this could indicate the direction of flow of data. Then we have a displacement, and finally a constant indicating the immediate data. There could be some exceptions in the addressing mode encoding, like immediate addressing mode, in which source register is specified to be a base pointer. Today we have discussed one example of a practical RISC processor, which was Spark, and 2 examples, one from Motorola and the other one from Intel for CISC processors. Now in the end, we should imagine and realize that the selection of instruction set architecture, which includes all the available resources, and the architect defines different addressing modes, this would ultimately affect the performance of the processor. And we have different options of either going to CISC or going to RISC. At present, as we saw, that most of the desktop processors use the CISC processors, and That is usually that we have more variety of instructions and we could just manipulate and do complex operations. Whereas in the case of RISC, the instruction count would increase. So ultimately, we have to strike a balance and see the two parameters. First one is the total instruction count. That means when a programmer is writing a program, and using RISC machine might mean a longer code, and using a CISC machine might mean a shorter code. And then the number of cycles, the clock cycles have on the average per instruction, that would dictate, and the clock cycle would dictate ultimately what is the execution time. So if the execution time could be reduced with RISC, that could be a choice. And if CISC architecture gives us a lower value of the final time which is required for execution of a particular program, that might be a better choice. So it depends ultimately also on the application. In the end, I will just summarize for today and say that we have considered the examples of both RISC and CISC, and with that, it would just give you a good feeling of the comparison of instruction set for a RISC, a practical RISC, and a practical CISC processor. That I hope is clear to you, and we will continue with the next phase, and that is the CPU design in our next lecture. For today, that's all, and Allah Hafiz till next time.